Welcome to the Machine Learning Crash Course. My name is Peter Norvig, and when I joined Google in 2001, my title was Director of Machine Learning, because I knew then that machine learning would be a valuable tool to help engineers at Google and everywhere else make sense of their data. I didn't quite anticipate then how widespread the tools would become and how much demand there would be for engineers who are skilled at using them. This course is designed to set you along the path to becoming a skilled practitioner of the art. What you learn here will allow you, as a software engineer, to do three things better. First, it gives you a tool to reduce the time you spend programming. Suppose I wanted to write a program to correct spelling errors. I could make my way through lots of examples and rules of thumb, like I before E except after C, and after weeks of hard work, come up with a reasonable program. Or I could use an off-the-shelf machine learning tool, feed it some examples, and get a more reliable program in a small fraction of the time. Second, it will allow you to customize your products, making them better for specific groups of people. Suppose I produced my English spelling corrector by writing code by hand, and it was so successful that I wanted to have versions in the 100 most popular languages. I would have to start almost from scratch for each language, and it would take years of effort. But if I built it using machine learning, then moving to another language to a first approximation means just collecting data in that language and feeding it into the exact same machine learning model. And third, machine learning lets you solve problems that you, as a programmer, have no idea how to do by hand. As a human being, I have the ability to recognize my friends' faces and understand their speech, but I do all of this subconsciously. So if you asked me to write down a program to do it, I'd be completely baffled. But these are tasks that machine learning algorithms do very well. I don't need to tell the algorithm what to do. I only need to show the algorithm lots of examples. And from that, the task can be solved. Now, besides these three practical reasons for mastering machine learning, there's a philosophical reason. Machine learning changes the way you think about a problem. Software engineers are trained to think logically and mathematically, and we use assertions to prove properties of our program are correct. With machine learning, the focus shifts from a mathematical science to a natural science. We're making observations about an uncertain world, running experiments and using statistics, not logic, to analyze the results of the experiment. The ability to think like a scientist will expand your horizons and open up new areas that you couldn't explore without it. So, enjoy the journey and happy exploring.
Hi, my name is Dee Scully. I'm one of the people who's coming to you from Google in order to present this machine learning crash course with TensorFlow APIs. Now, before we dive in, let's take a second to remind ourselves of the basic framework that we're talking about in this class. And that basic framework is supervised machine learning. In supervised machine learning, we're learning to create models that combine inputs to produce useful predictions, even on previously unseen data. Now, when we're training that model, we're providing it with labels. And in the case of, say, email spam filtering, that label might be something like spam or not spam. It's the target that we're trying to predict. The features are the way that we represent our data. So features might be drawn from an email as, say, words in the email, or to and from addresses, various pieces of routing or header information, any piece of information that we might extract from that email to represent it for our machine learning system. An example is one piece of data. For example, one email. Now, that could be a labeled example in which we have both feature information representing that email and the label value of spam or not spam. Maybe that's come from a user who's provided that to us. Or we could have an unlabeled example, such as a piece of email for which we have feature information, but we don't yet know whether it is spam or not spam. And likely what we're going to do is classify that to put it in the user's inbox or spam folder. Finally, we have a model. And that model is the thing that's doing the predicting. It's something that we're going to try and create through a process of learning from data. So as we said before, our model is something that we learn from data. Now, there are lots of complicated model types and lots of interesting ways we can learn from data. But we're going to start with something very simple and familiar, and this will open the gateway to more sophisticated methods. Let's train a first little model from data. So here we've got a small data set. On the x-axis, we've got our input feature, which is showing housing square footage. On our y-axis, we've got the target value that we're trying to predict of housing price. So we're going to try and create a model that takes in housing square footage as an input feature and predicts housing price as an output feature. Here we've got lots of little labeled examples in our data set. And we're going to go ahead and channel our inner ninth grader to fit a line. We can maybe take a look at our data set and fit a line that looks about right here, maybe something like this. And this line is now a model that predicts housing price given an input. We can recall from Algebra 1 that we can define this thing as y equals wx plus b. Now, in high school algebra, we would have said mx. Here we say w because it's machine learning, and this is referring to our weight vectors. Now, you'll notice that we've got a little subscript here because we might be in more than one dimension. This b is a bias, and the w gives us our slope. How do we know if we have a good line? Well, we might want to think of some notion of loss here. Loss is showing basically how well our line is doing at predicting any given example. So we can define this loss by looking at the difference between the prediction for a given x value and the true value for that example. So this guy has some moderate sized loss. This guy has near zero loss. Here we've got exactly zero loss. Here we probably have some positive loss. Loss is always on a 0 through positive scale. How might we define loss? Well, that's something that we'll need to think about in a slightly more formal way. So let's think about one convenient way to define loss for regression problems. Not the only loss function, but one useful one to start out with. We call this L2 loss, which is also known as squared error. And it's a loss that's defined for an individual example by taking the square of the difference between our model's prediction and the true value. Now, obviously, as we get further and further away from the true value, the loss that we suffer increases with the square. Now, when we're training a model, we don't care about minimizing loss on just one example. We care about minimizing loss across our entire data set.
Hi, my name is Cassandra Shaw, and I'm a programmer at Google that helps other groups within Google use TensorFlow. In this section, we're going to talk about reducing loss. Previously, we learned how to compute the loss, but how do we choose the set of model parameters that minimizes it? Well, what would be nice is if we had a direction to go in within parameter space, some sort of guide such that each set of new hyperparameters that we took on had a lower loss than the one before it. One way to get a direction is to compute the gradient, the derivative of the loss function with respect to the model parameters. For simple loss functions like the squared loss, the derivative is easy to compute, and it gives us an efficient way to update model parameters. Think of it as an iterated approach. Data comes in, we compute the gradient of the loss function on that data. The negative gradient tells us in which direction to update model parameters in order to reduce loss. We take a step in that direction, get a new version of the model, and now we can recompute the gradient and repeat. Pretend in one dimension, this is our loss function that maps our single model parameter theta to the loss. If we start off at a random value or initialization for theta, then we achieve the corresponding loss. We can then compute the negative gradient, which tells us in which direction we should go in order to minimize the loss. If we take a gradient step in that direction, we get a new loss. We can keep taking gradient steps in that direction until we reach a point in which we have passed the local minimum, in which the negative gradient will tell us to go back in the direction that we came from. How large of a step should we take in the direction of the negative gradient? Well, that is dictated by the learning rate, a hyperparameter that you can twiddle. If the learning rate is really small, then we'll take a bunch of teeny tiny gradient steps, requiring a lot of computation in order to reach the minimum. However, if the learning rate is very large, then we will take a large step in the direction of negative gradient, potentially overshooting the local minimum and even reaching a point in which the loss is even bigger than before. In more dimensions, this would cause your model to diverge, in which case you should try decreasing the learning rate by an order of magnitude or so. We just described an algorithm called gradient descent. We start somewhere and we continuously take steps that hopefully get us closer and closer to some minimum. However, does it matter where we start? Well, let's think for a minute. If we put ourselves back in calculus class, we learned that some problems are convex, meaning that they're shaped like a giant bowl. So as long as we start somewhere on the bowl and we take reasonable step sizes and follow the gradients, eventually we'll find our way to the bottom of the bowl. However, many machine learning problems are not convex. Neural networks are notoriously not convex, meaning that rather than being shaped like a bowl, they're shaped more like an egg crate, where there are many possible minimum values, some of which are better than others. So their initialization does matter. More on that later. Let's think for a moment about efficiency. When we're computing the gradient of the loss function, math suggests that we should compute the gradient over all examples in our dataset. This is the only way to guarantee that our gradient steps are in exactly the right direction. For large datasets with 1 million or billion examples, that would be a lot of computation in order to perform each step. Empirically, people have found that rather than using the entire dataset, if they compute the gradient of the loss function over a single example, that mostly works too. Even though they'd have to take more overall steps, the amount of total computation in order to reach a good solution is often much smaller. This is called stochastic gradient descent. In practice, we adopt an intermediate solution. Rather than use one example or the entire dataset, we use a small batch, somewhere between 10 and 1,000 examples, to perform our steps. This is called mini-batch gradient descent. As you likely know, TensorFlow is a platform that can be used to build machine learning models, but it's actually much more generic than that. It's a general graph-based computational framework that can be used to encode anything you can imagine. In fact, for the full list of low-level TensorFlow operations that are possible to use in your code, check out the API page under tensorflow.org. Contributors have also added a number of high-level frameworks that make it easy to do common tasks. You'll be interacting the most with the TensorFlow Estimators API that make it really easy to build neural network models.
So we mentioned before that just fitting our training data was not enough to be doing machine learning. In machine learning, we're really interested in generalization. Let's dive into that topic a little bit more. So here we've got a data set where we've got some spam examples here on the left and some not spam examples over on the right. If I wanted to, I could try and fit a linear model to sort of disambiguate the spam from the not spam. But any sort of linear model that I would try and fit here would end up making a little bit of error. Maybe this guy would be misclassified, or that guy would be misclassified as being on the wrong side of the line. And I might decide to try and be clever and get 100% accuracy on my training data by drawing a more complicated line. Maybe it would look something like this. I'm going to go and make sure that my model is going to be super clever and get 100% accuracy. All of my training examples are now completely correctly classified. What's the issue here? Well, the issue is, what if new examples are coming in? I might end up with some new examples that the model is just not really well suited to doing a good job on. So in a sense, this model has maybe overfit our training data originally, and it doesn't do a good job of classifying new, previously unseen data. Okay, so we've seen that if our models are too complicated, that overfitting is a real problem. How can we make sure that our models are not overfit in practice? Well, let's step back and take a look at the big picture of what it is we're trying to do in machine learning. At a very abstract level, we can imagine that there's some hidden process that is giving us data. And that hidden process might be something like the process by which emails are generated as either spam or not spam, and people label them as such through their perceptions, or the process by which pictures of puppies are generated and people label them as cute or non-cute. The process could be anything that gives us data, and in general, we're not going to know the full details of that process. The only thing we're going to know is the concrete examples that we get to sample from that process. So specific pieces of email or spam, specific pictures of puppies. We call those samples our data samples. Now, ideally, we would like to be able to train on a data sample and then know that it's going to do well on new draws from that hidden distribution. How will we be able to trust that? Well, one thing that we could do is we could use some nice ideas that go back as far as William of Ockham from the 14th century, our first machine learning theoretician, who developed the idea of Occam's razor, basically saying that a model should be as simple as possible. There's a whole field around this called generalization theory, and it's a fascinating field. We're not going to get into that too much in this course because we don't have to use theory. We can, in fact, use empirical stuff. And the empirical strategy we can use is to take another draw from that distribution and see how well we do. This is called using a test set methodology. So we pull one draw of data from that distribution, we train on that, that's our training set. We take another draw of data from that distribution, we call it our test set. And if we do a good job, about as well at predicting on our test set as we do on our training set, then we've got pretty good feeling that our model is going to be able to generalize well onto new, previously unseen data. Now there's a couple of caveats here. This is sort of the fine print of machine learning. The first is that we are drawing our data, are drawing independently and identically from that distribution. We're not biasing ourselves in any way. The second is that distribution is stationary. It doesn't change over time. And the third, kind of implied here, is that we're always pulling from the same distribution. We don't suddenly start pulling from a different one. Now, those are critical assumptions, and they sort of form the bedrock of a lot of what we do in supervised machine learning. But in practice, sometimes we do violate them. The stationarity assumption might be violated if, say, user behavior on shopping changes over the holiday season versus in the summer. And the pulling from the same distribution might change if people suddenly decide that a different breed of puppies is cute than they saw before. Fashions do change. So it's important for us to be aware of these assumptions and also to pay careful attention to our metrics anytime we know that these assumptions might be violated. Okay, let's talk a little bit more about that test set training set methodology. Now, what will happen if we only have one data set to work with? For example, we've got one big draw from our hidden distribution. Well, one thing we can do is we can divide that large data set into two smaller sets and use one for training and one for test. We need to keep them separate. It's also probably important to make sure that we do randomization before we do that splitting, so that we don't, say, by accident end up with all of the winter data in our training data and all the summer data in our test data. That would be bad. Now, how large should we make our different splits? Well, these are two things in tension. The larger we make our training set, the better model we're going to be able to learn. The larger we make our test set, the better we'll be able to have confidence in our evaluation metrics. We'll have tighter confidence intervals. If we have a very large data set, things are good. If we've got 1 billion examples, we might be able to still hold out 10 or 15% for a test and have strong confidence intervals there. If we have a very small data set, then we might need to do something a little bit more sophisticated, like cross-validation. Now, there is one classic gotcha that's worth bringing up, and this is that you do not ever want to train on your test data. This will give you unrealistically strong opinions about how good your model is. In particular, if you ever find yourself on that magic day when you have 100% accuracy on your test data, double check that you have not made a mistake and have accidentally trained on your test data. This can happen. It happens to everybody at one point or another. So before you celebrate and throw a party, double check your data. So now we have this powerful test and training set methodology. So let's imagine that we're using it in practice. We've got our test set, we've got our training set, we did a good job of separating them out. And we're going to now do some iterations. I'm going to train a model on my training data, I'm going to test it on my test data, and I'm going to observe its metrics. And I'm going to tweak some setting. Maybe I'm going to tweak the learning rate or something like that. I'm going to try again and see if I can improve my test set accuracy. Maybe I'm going to add some features in. I'm going to take those features out and keep iterating and iterating till I find the best possible model that I can based on my test set metrics. Are there any problems here? Well, one thing I could imagine is that maybe I'm starting now to overfit to the peculiarities of my test data. That's too bad. So here's another way to handle that. I can create a third data set out of my partitions. And I'm going to call this my validation data. And I'm going to use a new slightly augmented iterative approach, where I'm going to do my iterations by training on my training data, and then evaluating only on my validation data, keeping my test data way off to the side and completely unused. And I'm going to iterate and iterate, tweaking whatever parameters or making whatever changes I want to my model until I get very good data, very good results on my validation data. I'm then, and only then, going to test my model on the final test data. And I'm going to make sure that the results that I'm getting on the test data basically match what I'm getting on my validation data. If they don't, that's a pretty good signal that maybe I was overfitting to the validation set. So what's interesting is that when we work with data in the real world, it doesn't come to us as nicely formatted feature vectors. Instead, it comes to us as database records or protocol buffers or whatever else. We need to take that data from those heterogeneous data sources and create feature vectors from it. Now, the process of extracting features from raw data is called feature engineering. And it's what real-life machine learning people spend, I don't know, something like 75% of their time doing. The features are the thing. So let's take a look at how this might happen. If we have a record that is naturally represented as a real value, like number of rooms in a house, we can just copy that over into a feature vector. And that's very natural. But what if we get a string, like Main Street? What do we do then? If we see a string value, we can often translate that into a feature vector by using a one-hot encoding. Now, the one-hot encoding has a unique coefficient for each possible string we might see. So, for example, if we have a one-hot encoding for street names, we'll have a unique coefficient for each possible street. And then when we see this street we have, say Main Street, we'll put a 1 in the coefficient for Main Street and a 0 everywhere else. Don't worry, we can represent that compactly, and we'll use that as our feature vector for representing strings. One-hot encodings are extremely handy for this sort of sparse categorical data. Now, what makes a feature a good feature? Well, the first thing is that a feature should occur with a non-zero value at least a handful of times or more in our data set. If a feature occurs with a non-zero value only extremely rarely, or maybe only once, it's probably not a great feature to use and should maybe be filtered out in a pre-processing step. Our features should have a clear and obvious meaning. This allows us to do good sanity checking and debugging to make sure that our features are being processed properly. For example, it's much easier to have a house age in units of years than a house age in seconds since Unix epoch. Much easier to debug and reason about. So features shouldn't take on magic values. So for example, it would be a bad idea if we had a feature whose job it was to tell us how many days a house had been on the market, for us to use a special value of -1 to show that that house had never been on the market. Instead, a better idea would be to have an indicator feature that would take on a Boolean value showing whether our days on the market feature was defined or not. So we could have Boolean true false 1 0 to show is that other feature defined. And this allows the original feature, days on the market, to maintain its natural units of 0 through n. The third thing is that our feature values shouldn't change over time. This goes back to the idea of stationarity in our data. Now, why might a feature value change over time? Well, maybe our features come to us from some upstream model that might change. We'd like to be able to version that and have a very specific sense, or to be able to get values out of that model that really do have well-defined constant semantics. Last thing is that a feature should not have crazy outlier values. So for example, in our California housing data, if we create a synthetic feature, like rooms per person, where we take the total rooms and divide it by the total population, we get some reasonable values of between 0 and 3 or 4 rooms per person for most city blocks. But on some city blocks, we've got values as high as 50, which is insane. I mean, where are these people living? Like hotel blocks? So a thing we can do there is maybe cap or transform our features so that we get rid of those crazy outlier values. One other trick to think about is the binning trick. So if we think about, say, the effect of latitude on housing prices in California, there is no sort of linear relationship from north to south that maps directly to housing prices. But within any particular latitude, there often is a pretty strong correlation. And so what we can do is we can take that north to south latitude and bucket it up into a bunch of little bins. These each become Boolean features. We can use a one-hot encoding here. And essentially what we get is a 1 now if you are in the particular bin that maps to, say, San Diego, or a 1 if you're in the particular bin that maps to the South Bay Area, and a 0 everywhere else. This allows our model, a cheap way to map some of those nonlinearities into our model without doing any special tricks. So let's think about some good habits here. It's incredibly important to know your data. It's not really a good practice to just sort of treat machine learning as a black box, throw it at data without inspecting the data and hope you get good results, because there will be quirks in your data. So things you can do. You can visualize your data using histograms or scatter plots, various rank metrics. You can do various data debugging that ends up consuming a lot of time for model development, looking for duplicate values, missing values, anything that looks like an outlier, anything that looks like a dashboard that you can interact with your data can be incredibly helpful. And finally, we want to monitor our data over time. Just because our data sources were good yesterday does not mean they're going to be good tomorrow. And so anything we can do to add monitoring to the stability of our features over time will increase the robustness of our systems. Let's start off by looking at a linear problem. You'll recall that a linear problem is something where we can fit a line to separate, say, this spam from the not spam, depending on a couple of input variables. Here we've got two input variables, x1 and x2. These are our input features. And we've got a linear model here of w1x1, w2x2, and a bias term. Now this is easy to fit, right? However, what if our model needed to model something more complicated? In particular, what if our data, in fact, looks more like this? In this world, there's really no way for us to fit a simple linear model that's going to get anything more than about 50% accuracy. What can we do? Well, one clever idea is that we could define an additional feature. We're going to call this a synthetic feature or a feature cross. We're going to do it like this. We're going to call it x3. We're going to define x3 as the product of x1 and x2. Now, can I use x3 in my linear model? Yes, indeed, I can. I'm going to go ahead and add a coefficient, w3, for x3. And you'll notice that the product of x1 and x2 is always positive if they're both positive, or if x1 and x2 are both negative. So I get this very nice ability to pull out my blue dots if the product of x1 and x2 is positive. Similarly, we'll always have a negative if either one of these coordinates is negative. So this allows us to learn a nonlinearity within a linear model using a simple synthetic feature that's called a cross product. So the general name of this process of creating synthetic features as products of other features, we call feature crosses, feature cross products. We can think of these as maybe templates of the form sort of A cross B. They could be complex, A cross B cross C cross D. And when A and B are Boolean features, things that we might get from a one-hot encoding, like various strings or bins, the resulting crosses might be quite sparse. That one-hot encoding may have an awful lot of zeros in it. Let's think of some additional examples here of where feature crosses might be useful. So if we're predicting housing prices in California, we might want to say cross latitude or binned latitude with the number of bedrooms. And this would allow us to learn that maybe having 3 bedrooms in San Francisco is a very different thing from having 3 bedrooms in Sacramento. You could also think about a tic-tac-toe predictor. And you might think of the cross products that you would be able to use there by crossing the various coordinates in the tic-tac-toe grid. Because obviously an X or an O in any particular segment of that tic-tac-toe grid by itself isn't very interesting. But to be able to say your left corner, center, right bottom altogether is a very different thing. So why would we want feature crosses? Well, The main thing is that this allows us to incorporate nonlinear learning into a linear learner. Now, linear learners are very interesting to us because they scale very naturally to massive scale data sets. In fact, for many years, linear learners were the only method that we really had that would scale to billions or hundreds of billion sized data sets. Now, we also have deep neural networks that can scale well. So that's another option that we'll look at later on in this class. Finally, there's been some interesting research showing that combining the effects of linear learning through feature cross products and deep networks can be extremely powerful for modeling.
Hello, I'm Maya Gupta. I'm a machine learning researcher here at Google, and I'm excited today to talk about the second key ingredient to making machine learning work great. You guys have already talked about minimizing training loss, that is, getting the examples right. And what we're going to talk about today is regularization, which, to sum it up, is not trusting your examples too much. As we can see in this curve called overfitting, as we go through more and more training iterations, our training loss is getting down. It's getting further and further down, and it keeps decreasing because that's what we're doing. We're minimizing the training loss. So no surprise that the blue curve keeps going down. Eventually, it'll sort of converge there. But the red line actually starts to go up. And the red line is what we really care about. We want to generalize. Even though we're training on the training examples, we want to generalize to new examples, the test examples, and we want to have low loss on them. So how do we keep the red line from going up, and what's going on here? Well, first of all, what's going on is overfitting. We're doing such a good job on the blue examples that we're starting to sort of fit to the unique perturbations and specializations of the blue examples. As an analogy, say you were trying to learn English and the only person that there was to teach you English was a teenager. At first, that would really help you learn English and you do a great job learning English. But if all you did was listen and talk to that one teenager, pretty soon you'd start to learn that teenager's slang and the particularities of their language and accent. And at some point, it'd make it even harder for you to speak English with the general population. So what can we do about overfitting? Well, regularization is what we do to avoid overfitting. And there are a lot of different regularization strategies. One is just to do early stopping, which says just stop the training before you've really converged on the training data, trying to get to where the bottom of the red curve is. But this can be a little difficult to do in practice, but often used. Other regularization strategies include trying to penalize the model complexity, and that's what we'll be talking about the rest of this section. And what we can do is we can penalize the model complexity while we're training. So far, the training has just focused on the important thing of getting the training examples right, minimizing the empirical risk minimization. Now what we're going to do is we're going to add a second term to penalize the model complexity. This is sometimes referred to as structural risk minimization. And so we're going to balance these two key ingredients, getting the training data right, but not trusting the training data too much that it makes our model too complicated. So how do we define model complexity? Well, there are a lot of things we could do. One popular strategy is to try to prefer smaller weights. That is, make the parameters as small as we can get away with while still getting the training examples right. And we could encode that mathematically in a few different ways. Today we're going to focus on L2 regularization, also known as ridge regularization. In this regularization strategy, we penalize the sum of the squared values of the weights. And if you're familiar with Bayesian priors, this sort of says that a priori, before we've seen our training examples, we would have guessed that our weights should be sort of centered around 0 and not too big, normally distributed. So when we use L2 regularization, it does pay attention to the training data, but it tries to make sure that we don't end up with any weights that are sort of bigger than they need to be. So let's put that together mathematically again. So now our training optimization has two terms. The first term, our training loss. We want to get the examples right. And you'll see that L term, the loss term, depends on the training data. But now we've added the second term for model complexity, and here we're using the L2 regularization, which is the sum of the squared weights. And you'll notice that that second term doesn't depend on the data. It just says, hey, I want a simple model. And you'll see these two terms are balanced by a lambda. That's a coefficient that says, how much do we care about getting the examples right versus making the model simple? And the choice of lambda is really up to you and depends on your problem. If you have lots and lots of training data, and your training data and your test data look the same, IID to be statistical, then you probably don't need much regularization, maybe 1e to the -6, maybe none at all. But if you don't have much training data, or if your training data and test data are kind of different, then you may want a lot of regularization. And you may want to tune that with cross-validation or with a separate test set.
Let's imagine for a second that we've got the problem of predicting the probability of heads for some coin flips where maybe the coin is slightly bent. You might use features like angle of bend, coin mass, all kinds of stuff in there. What's the simplest model you could think of using? Well, we could maybe use linear regression like we've used before. But there might be some weird things there. For example, what if we have a new coin that we're predicting on that has a very heavy mass we've never seen before? Or what if we have an extremely large bend of the angle? We might end up with predictions that are outside the range 0 to 1. That would be really weird for probabilities, because probabilities are a special thing. Probabilities are bounded between 0 and 1. And if we have a prediction model that gives us a value outside that range, we're going to be in trouble, especially if we say try and multiply predicted probabilities or use them to create expected values or stuff like that. Well, as a first hack, you could try and cap that prediction to ignore any outlier values. But now we've introduced bias into our model, and we're not going to be very good there. So really the right thing to do is to come up with a slightly different loss function and prediction method that allows our values to be interpreted naturally as 0 to 1 probabilities and never exceeds that range 0 to 1. So we call this idea logistic regression. It's a prediction method that gives us well-calibrated probabilities. And these are fantastically useful. We can use these as real probabilities and multiply them with things to get expected values, and use them also for things like classification tasks, where we really want to know the real probability that an email is spam or not spam. So let's take a look at how this might work. We take our familiar linear model and we stick it into a sigmoid. And a sigmoid is basically something that gives us a bounded value between 0 and 1. There's asymptotes, so it never quite hits 0 and it never quite hits 1. At training time, we're training using a different loss function. As we said, squared loss is not going to cut it here. We use something called log loss, that if you squint closely at the formula there, it looks very similar to Shannon's entropy measure from information theory. Now, you don't need to understand the math to be able to take a look at the graphical interpretation, where you'll notice that as you get closer and closer to one of the bars, the loss gets very, very high quite quickly. Again, we see those asymptotes coming into play. So those asymptotes are actually quite important to think about in terms of learning. Because of those asymptotes, we will need to really incorporate regularization quite explicitly into our learning. If we don't, then on a given data set, the model may try and fit our data ever more closely, trying to drive those losses near 0. So L2 regularization can be extremely helpful here to make sure that our weights don't go crazy out of bounds. Why do we like linear logistic regression? Well, one thing is that it's really fast. It's extremely efficient to train, and it's efficient to make predictions. So when we need a method that scales well to massive data, or that we need to use for extremely low latency predictions, linear logistic regression can be a great choice. If we need nonlinearities, we can get them by adding in feature cross products. So we've talked a lot about regression, but sometimes what we want to do with a machine learning model is make a classification. Is it A or not A? Is it spam or not spam? Is the puppy cute or not cute? Now we can use logistic regression as a foundation for classification by taking our probability outputs and applying a fixed threshold to them. For example, we might decide to mark something as spam if it exceeds a spam probability of 0.8. That 0.8 is our classification threshold. Now, once we've chosen to make a classification threshold, how are we going to evaluate the quality of that model? We need some new metrics. Our regression metrics aren't sufficient. One classic way of evaluating classification performance is to use accuracy. And by accuracy, we mean count all the things you got right and divide it by all the things that there were. It's basically what percentage of the things did you get correct. Interestingly enough, even though accuracy is a very intuitive and widely used metric, it has some key flaws. In particular, accuracy breaks down when we have class imbalance in our problems. Imagine if we were to try and use accuracy to assess the quality of a model that is predicting ad click-through rates for display ads. In display ads, our click-through rates are often 1 in 1,000, 1 in 10,000, or even lower. So I might have a model that has absolutely no features in it, except for a bias feature that tells it to predict false always. This predict false always model would have an accuracy of 99.999% in display ads predictions, but would add absolutely no value. Clearly, accuracy is doing something wrong here. So to deal with class imbalance problems, we need a more fine-grained way of looking at the way that our models predict on positives and negatives, or different classes. So we can think about these different kinds of successes and different kinds of failures along a 2x2 grid that has true positives, false negatives, and true negatives. To help us understand these, let's remember the story of the little boy who cried wolf. Now, this little boy is a shepherd, the wolf comes to town. If he correctly spots the wolf, that's a true positive. He sees the wolf, he says, "Wolf!" True positive, saves the town. Good job. Now, a false positive is when that little boy says wolf, but there really wasn't a wolf. That is a false positive. It makes everybody annoyed. A false negative may be even worse. A false negative, there was a wolf coming along, and the little boy was asleep or didn't see it, and the wolf went in and ate all the chickens. That's really no good at all. A true negative is when the boy did not cry wolf, and indeed there was no wolf. Everything's fine. So we can combine these ideas into a couple of different metrics. One of them is precision, which is when the little boy said wolf, how many times was he right? How precisely was he able to say wolf? Recall, on the other hand, is of all of the wolves that tried to come into the village, how many did we get? Now, what's interesting is that these things are often in a little bit of tension. Because if you imagine that you want to do a better job at recall, the right thing to do is to be more and more aggressive about saying wolf, even when you just hear like a little noise off in the bushes. So we can think of that as lowering our classification threshold. But if we want to be really precise, the right thing to do is to only say wolf when we're absolutely sure. So we might think of that as raising our classification threshold. So these two metrics are often in tension, and doing well at both of them is important. It also means that whenever someone tells you what the precision value is, you need to also ask about the recall value before you can say anything about how good the model is. Now, precision and recall are both well defined when there is one specific classification threshold that we've chosen. But we might not know in advance what the best classification threshold is going to be. And we still want to know if our model is doing a good job. Well, a reasonable thing we could do would be to try and evaluate our model across many different possible classification thresholds. And in fact, we have a metric that looks at the performance of our model across all possible classification thresholds. And this is called an ROC curve, Receiver Operating Characteristics Curve. And the idea is that we evaluate every possible classification threshold and look at the true positive and false positive rates at that threshold. We then draw a little curve that connects those dots, and the area under that curve has an interesting probabilistic interpretation. It goes like this. If I were to pick a random positive example, closing my eyes, I pick one out of our distribution, and I pick a random negative example, what's the probability that my model will correctly assign a higher score to the positive than it does to the negative? In a sense, what's the probability it gets that little pairwise ordering correct? Turns out that that probability is exactly equal to the probability value of the area under the ROC curve. So if I see a value of 0.9 area under ROC, that's the probability that I will get that pairwise comparison correct. One last measure to think about is prediction bias. Now, prediction bias is defined by taking the sum of all of the things that we predict and comparing them to the sum of all the things we observe. Basically, we would like the expected values that we predict to be equal to the observed values. If they're not, we say that the model has some bias. A bias of 0 would show that the sum of the predictions equals the sum of the observations. Now, bias is a very simplistic metric in that it's easy to fool. We could have a model that has almost no value to it. It just predicts the mean of all the class probabilities to create a zero bias model. However, it's a useful canary, because if one of our more complicated models does not have zero bias, it means that something is going on. It gives us something to dig into as a way to debug our models. So if our model does not have zero bias, it's definitely cause for concern and allows us to maybe slice the data and see what areas the model is not doing a good job of having zero bias on. However, just having zero bias by itself is not an indicator that the model is perfect. We need to keep looking at other metrics for that. We can look at more fine-grained views of bias by looking at a calibration plot. And with a calibration plot, what we do is we take groups of data, we bucket them up, and look at the mean prediction versus the mean observation for things in that bucket. Obviously, we do need to have buckets of data to make calibration be meaningful. For example, if I'm looking at flipping a coin, any given coin flip will either come up exactly heads or exactly tails, basically exactly 1 or exactly 0. But my probabilistic predictions will be 0.5 or 0.3 or some value in between 0 and 1. So it only makes sense to compare those mean predictions to mean observations if I aggregate across a sufficiently large number of them.
So let's dig a little deeper into feature crosses. They can be great, but they can also cause some problems. In particular, for crossing sparse features. For example, maybe one of our features is the words in a search query, and the other feature might be the unique videos that we have to look up. So now we have maybe millions of possible words, maybe millions of possible videos, and we're crossing those, we're going to get a lot of coefficients. All of that means that our model size is going to explode, taking memory, possibly slowing down runtime, and a lot of those combinations are going to be super rare, even if we have a lot of training data, and so we may just end up with some noisy coefficients and possibly overfitting. So you know the answer. If we're overfitting, we want to regularize, and now we're going to say, can we regularize in a way that also will reduce our model size and our memory usage? So what we'd like to do is just try to zero out some of the weights, in which case we won't have to deal with those particular crosses. This could save us RAM, and this can also potentially help us with overfitting. But we have to be a little careful. We don't want to lose the right coefficients. We just want to lose the ones that are sort of extra and noisy. So what we'd like to do is explicitly zero out weights, and that's what we call L0 regularization. It would just penalize you for having a weight that was not 0. But that's not convex. It's hard to optimize. It's sort of a combinatorial problem. Instead, what we do is we relax that to an L1 regularization, which just penalizes the sum of the absolute values of the weights. And by doing that, we still encourage the model to be very sparse. It'll drive a lot of those coefficients to 0. And that's a little different than L2 regularization, which also tries to make the weights small, but won't actually drive them to 0 for you.
At this point, we should recognize this problem as a simple nonlinear problem, something that we can solve easily with feature cross products. But what happens if we get a slightly more complicated problem, maybe something that looks like this? At some level, we've got maybe a set of spirals interacting with each other. Now, we could probably sit around and do some math and think of the right feature cross products to add, but it's easy to think that our data sets might be more and more complicated, and eventually we would like some way for our models to learn the nonlinearities themselves without us having to specify them manually. This is the promise of deep neural nets that do an especially good job at complex data, including image data, audio data, and video data. We'll learn more about neural nets in this section. So we'd like to have models that learn the nonlinearities themselves without us having to specify them manually. How are we going to do that? Well, we probably need a model with some additional structure to it. Let's take a look at our linear model, where we have a number of inputs, each with a weight that's combined linearly to produce an output. Well, if we want to get a nonlinearity in there, maybe we need to have an additional layer in there. So now we can add those guys up in a nice linear combination into a second layer. That second layer gets linear combined, and we haven't yet achieved any nonlinearity because a linear combination of linear functions is still linear. Okay, well, that's not good enough. So clearly what we need is a second layer, right? So we put a second layer in there, and we're still linear, because even if we add as many layers as we want, any linear combination of linear functions is still going to be linear. Okay, we need to do something else. And that something else is we need to stick in a nonlinearity. That nonlinearity can go at the output of any of our little hidden nodes in there. One common nonlinearity that we use is called ReLU. And this takes a linear function and chops it off at 0. So if you're above 0, you're a linear function. If your function returns a value below 0, we cap that at 0. Simplest possible nonlinear function, and this allows us to create nonlinear models. Now, we could use any nonlinearity in here. A lot of folks also use sigmoid or tanh, but it turns out that ReLU gives state-of-the-art results for a wide number of problems, and it's very simple. Once we have this, we can stack these layers up and we can create arbitrarily complicated neural networks. Now, when we train these neural nets, obviously we're in a non-convex optimization, so initialization may matter. The method that we use for training these is a variant of gradient descent called backpropagation. And backpropagation essentially allows us to do gradient descent in this non-convex optimization in a reasonably efficient manner. So when we think about how to train neural networks, what do you need to know about, say, backpropagation? Well, one thing you don't need to know about backprop is how to implement it. That's one of the brilliant things that TensorFlow does for us, is it takes the internals of backpropagation and does that all for us underneath the hood. But there are some important things to know. The first is that backprop really does rely on this idea of gradients. Things need to be differentiable for us to be able to learn on them. One or two small discontinuities in our various functions are fine, but in general, we need differentiable functions to be able to learn with neural nets. Another thing is that gradients can vanish. If our networks get too deep, sort of signal-to-noise ratios get bad as you go further and further down the model, and learning can really become quite slow. ReLUs can be useful there. There are also some other strategies that we won't talk about in this class. But in general, you do want to think about limiting the depth of your model to sort of the minimum effective depth if you can. It's also important to know that gradients can explode. If our learning rates are too high, we get these sort of crazy instabilities. We can get NANs in our model. The thing to do there is to try again with a lower learning rate. Last thing to know is that ReLUs can die. It's possible that because we have this hard cap at 0, if we end up with everything below that value of 0, then there's no way for gradients to get propagated back through, and we'll never be able to pull ourselves back up into the land of living ReLU layers. So keep an eye out for those, and again, try again with a different initialization or a lower learning rate. At training time, it's often very useful for us to have normalized feature values when they come in. If things are on roughly the same scale, this can help speed the convergence of neural nets. So the exact value of the scale doesn't really matter. We often recommend -1 to +1 as an approximate range. It could be -5 to +5 or 0 to 1. It doesn't really matter so long as all of our inputs are on roughly the same scale. Finally, one last trick that's useful in training deep networks is the idea of an additional form of regularization that is called dropout. And dropout is kind of a funny idea. When we apply dropout, what we're saying is that with probability p, we take a node and we essentially remove it from the network for a single gradient step. On different gradient steps, we repeat and we'll take different nodes to drop out randomly. So the more you drop out, the stronger regularization you have. And you can kind of see this clearly where if you drop everything out, you have an extremely simple model that is essentially useless. If you drop out nothing, you allow the model to have its full complexity. And if you have dropout somewhere in the middle, you're applying some sort of useful regularization there. Dropout is one of the key advances that has enabled a number of the strong results that we've gotten recently that has pushed deep learning to the forefront. So up until now, we've talked about classification for binary class problems. Is something spam or not spam? Is the puppy cute or not cute? And logistic regression with a classification threshold is very well suited to these sorts of binary class classification problems. But in the real world, we're often not choosing just between two classes. Sometimes we need to pick a label out of one of a range of classes. For example, is the object animal, vegetable, mineral, or man-made object? Is the color red, orange, green, blue, indigo, or violet? Do we have a picture of an apple, a car, a banana, a dog, blah, blah, blah? There's lots of areas where being able to do good multi-class classification is a useful thing. Now, interestingly enough, we can build off of some of the technology that we already have with binary class classification. One classic way of doing this is through the one versus all multi-class classification. So essentially what we do is we have one logistic regression output node in our model for every possible class. So one node might identify, is this an apple? Yes, no. Another might say, is this a picture of a bear? Yes, no. A third might say, is this candy? Yes or no. And we have one output node for every possible class that we're looking at. We can do this in a deep network by having different output nodes at the outset of the model and share the internal representation through the rest of the model. So these can be trained reasonably efficiently together. In some problems, we know that an example will belong to only one class at a time. For example, a given fruit is either a banana or a pear or an apple. In this case, we'd like the sum of the probabilities of all of our little output nodes to sum to exactly 1. And this can be achieved by using something called softmax. Softmax is essentially a generalization of the same logistic regression that we used, but generalized to more than one class. When we have a single label multi-class classification problem, we use softmax. This encodes some helpful structure to the problem and allows us to use those outputs as well-calibrated probabilities. In other cases, we might have a multi-label classification problem. For example, an image might contain both an apple and a banana in it, or might contain 3 different dogs, or a dog and a person. And we'd want to be able to identify all of those different labels in the same example. And in that case, we do need to use a one versus all classification strategy, where each output is computed independently, and the outputs do not all necessarily sum to 1. When we're training a multi-class classification, we've got a couple of options here. We can use full softmax, just straight out of the box, and this is relatively expensive to train. You can think if you have 1 million classes, then you essentially needed to train 1 million output nodes for every single example. Now, it's possible that if you're trying to disambiguate between the dog being a Labrador and a poodle, that knowing that it's not a toaster is actually quite an easy thing. And so we can be a little bit more efficient there by doing something called candidate sampling, where we train the output nodes for the class that it belongs to, and then we take a sample of the negative classes and only update a sample of the output nodes. This is quite a bit more efficient at training time. It doesn't seem to hurt performance very much in a lot of cases. Obviously, at inference time, we still need to evaluate every single output node.
Hi, I'm Sally Goldman, and I'm a research scientist at Google. And one of the main things I work on is recommendation systems. And one thing really fundamental to doing these recommendation systems is embeddings. And I'm going to talk about those today. As a motivating example, I'm going to look at the problem of collaborative filtering. So let's say I have 1 million movies, and I have 500,000 users, and for each user, I know which movies that user has watched. The task is simple. I'd like to recommend movies to users. To solve this problem, I'm really going to have to learn some structure, something that let me say these movies are similar to each other. So if you've watched these 3 movies, then this is a good movie to recommend. So as a simple starting point, let's try to take these movies and just put them along a line, a one-dimensional embedding. So I will say I have maybe to the left, I'll put animated movies. And as I move to the right, I'll have more adult-like movies. This starts to do nice things. I have Shrek and The Incredibles. Those are both animated movies for kids. And if you watch one, the other one is a good recommendation. But then I have The Triplets of Belleville, which is an animated movie. But really, Harry Potter, though not an animated movie, I think is really a much closer movie to Incredibles. The Triplets of Belleville is not really oriented for kids as much. It's not sort of a blockbuster movie that a lot of people go to see. And on the other side, for example, I'd say Blue and Memento are probably better recommendations for each other than The Dark Knight Rises. So just having a single line, as much as I try, it's going to be really hard to capture all the intricacies in movies that make people like one versus another. So what if we add another dimension? And now I have 2 dimensions. So what if I bring the blockbuster movies up towards the top and the more art house movies down? Now I've achieved some of the things I've wanted. I've got Shrek and Incredibles and Harry Potter kind of nearby, and they're all pretty similar movies. And in the bottom right, I have Blue and Memento. And you can imagine that there's a lot of other aspects you'd want to capture, and you'd want more than 2 dimensions. And we would. In reality, we could imagine 20, 50, even 100 dimensions to sort of do these embeddings. But let's stick with 2 dimensions because I can draw it. So let's add a few more movies to this. And I went ahead and added some axes. I have the x-axis, which is sort of more children-oriented movies to the left, and more adult movies to the right. And the y-axis, more blockbuster movies to the top, and more art house films on the bottom. And you can see a lot of nice structure here. And you can see that movies nearby each other are kind of similar. And that's really the goal of what we want. Now, I'm drawing this geometrically, but I do want to make sure everyone understands that there's a very simple way to represent these embeddings, and that's what's going to happen when I learn them in a deep neural network. So just using Shrek and Blue as an example, each of these is just a single point in this two-dimensional space, and the way we write down a point is just the value on the x-axis and the value on the y-axis. So for example, Shrek is just the point -1, 0.95, or Blue is 0.65 minus 0.2. So each movie here can just be represented as two reels. And the similarity between movies is now captured by how close these points are. And although I'm only going to draw 2 dimensions, in reality, you do want to do this in d dimensions. 2 isn't going to be enough to capture everything. Implicitly, as you think about what you're doing, this is really assuming that interest in movies can be captured by d dimensions. I'm allowing d different aspects to be selected, and then I can move the movies independently among these d aspects and use that to now bring similar movies nearby to each other. Each movie now is just a d-dimensional point. I can write it down as d real values. And the cool thing is we can actually learn these embeddings from data, and we can do this with a deep neural network without adding a lot of new things to what you've already seen. There's no separate training process needed. We're just going to use backpropagation exactly as before, and the embedding layer is just a hidden layer. And we'll have one unit for every dimension you want in your embedding. Supervised information is going to allow us to tailor these embeddings for whatever task you're after. If you want to do movie recommendation, then we want these embeddings to be geared towards recommending movies. We'll need some sort of training signal. We'll look at some concrete examples, but in this example, if a user has watched a set of movies, then to some extent those movies are similar to each other and should be nearby. And we'll aggregate this, of course, over lots of data. Intuitively, these hidden units are learning how to organize the data in a way to optimize whatever metric we've decided to put as the final objective of the network. So now let's go back and look at how would this actually be input to the neural network. The matrix I show on the right is sort of the classic way we think of collaborative filtering input. I have one row for every user, and one column for every movie, and a check in this simple case indicates the user has watched the movie. So now let's think about how we do this within TensorFlow. Each example is really just going to be one row of this matrix. So let's focus on the bottom row that I've highlighted in yellow. If there's 500,000 movies, I don't really want to list all the movies you haven't watched. It's so much more efficient to just write down the movies you have watched. And when I do backpropagation, I'll be computing dot products, and I'd like that also, the time, just to depend on the movies you have watched. So to achieve this, we're going to use the following input representation. And to do this, we're going to have 2 phases. The first pre-processing phase, we're going to build what we call a dictionary. A dictionary is just a mapping from each feature, in this case each movie, to an integer from 0 to the number of movies minus 1. So I'll just do this in the order I've shown them in the column. So column 0, I'll call movie 0, column 1, movie 1, and so on. And this is a one-time thing we do, is pre-processing. Now I can efficiently represent that bottom example as just the 3 movies that user did watch. I don't need to worry about all the other ones. I drew it kind of as a pictorial view, but in reality it's just 3 integers. 1, 3, 999,999, because those are the indices for the 3 movies that user has watched. Okay, so now that we have the input representation, we can now look at how this fits into the full network, and I'm going to use 3 different examples to help illustrate it. The first example I want to look at is the problem of predicting a home sales price. So this would traditionally be done as a regression problem. I'd like to optimize the squared loss between the predicted price and the true sale price. So the thing that I really would like to create an embedding layer for here are the words in the sale, the house description ad. Because although they're a set of words, I really need to understand what words are similar in terms of figuring out the size of the house. So I may say this is a spacious house, or I may say it's roomy. Those are words that are used that kind of capture the same thing. And so I want to begin understanding how these words that real estate agents put in ads help us understand something about the home. So we have lots and lots of words that might be in an ad. In any given ad, I don't know, what has 100 words or so. And so again, we really do want the sparse embedding, just like we talked about, but my vocabulary is over words versus movies. I'm going to learn a three-dimensional embedding in this little toy example just so I can draw it. Again, in reality, you'd probably want a lot more than 3 dimensions. And I'm always in these examples going to draw my embedding layer as green. It's really a hidden layer, in this case 3 units, because I want a 3-dimensional embedding. I also may have other input data, like the latitude, longitude, number of rooms, and you can add all of that. I've just used latitude and longitude as an example. And then in pink, I'm showing the fact that we can have whatever other hidden layers we want. These are just your standard hidden layers. You can have as many as you want. You can decide how many units. And then at the end, they'll go into a single unit that, since the regression problem will give us a real value, and we'll optimize the L2 loss with the sale price. In the process of doing backpropagation, just like you've seen, the embedding layer will be learned. As another example, suppose I want to learn to classify handwritten digits. So I have the digits 0 to 9, and I have some training data where there's actually a label of the correct digit. So here, the sparse thing I want to create an embedding of is just the raw bitmap of the drawing, whether there's a white or black, so 0 or 1. I can introduce whatever other features I'd like. And again, I have an embedding layer, which I'll stick with keeping them 3 dimensions. So the representation of the digit will go into that. In pink, I show we can have whatever additional hidden layers. And in this case, we'll have a logit layer. We're going to have the 10 digits and basically learn a probability distribution over the digits of how probable we think it is that this is each of the digits. I can take the one hot target probability distribution from what I know the right answer is and optimize the softmax loss. In the process of doing this and training it with backpropagation, I will learn to embed the images. And now let's look at the example we've been studying of collaborative filtering, the movie recommendation problem. This is actually interesting. It brings up an aspect we haven't seen yet, which is, where is my training data here, right? I just know for each user there's a set of movies. So how do I know what the right movie to recommend is? What am I going to use as the label? What we'll do is, suppose a user's watched 10 movies. We'll use a simple trick. We'll randomly pick 3 movies and hold those out. Take them away, and those are the labels. So those are the movies I like to recommend. They're good recommendations because you watched them. And I'll take the other 7 movies and use them as my training data. Once I've done that, this is very similar to what we just talked about with the character recognition. I'll take the 7 movies that are my training data. We know how we can get the sparse representation. We'll bring them into the embedding layer. We can take whatever other features we want, maybe the genre, maybe the director, whatever else we want to take about the movie or the user. And then we can bring those into additional hidden layers, and we'll have a logit layer. And note this logit layer is big. Instead of 10 different nodes like in the character, the digit prediction, this, if I have 500,000 movies, there's going to be 500,000 of these. There's issues with that. It's out of the scope of this discussion, but we will get a distribution over those 500,000 movies of what movies we think you'd like. We will then optimize the softmax loss with the held out movies that we know you do like. And in doing this, in the backpropagation and just the standard training, we will learn the embeddings of the movies like we talked about. So I do want to come back now and just make sure it's clear how what we learned in the deep neural network ties to the geometric view I gave at the beginning. Let's look at the deep network on the left, and let's take a single movie, right? If you think of the input layer, each of those nodes at the bottom represent as one of these 500,000 movies. I've picked one movie and just made it black. In this example, I said I had 3 hidden units, so I was learning a 3-dimensional embedding. So that black node will have an edge connecting it to each of those units. I used red for the first one, magenta for the second, and brown for the third one. When you're done training your neural network, those edges are weights. Each edge has a real value associated with it. That's my embedding. The red is my x value, the magenta is my y value, and the brown is the z. So this particular movie would be embedded in a three-dimensional space as 0.9, 0.2, and 0.4. As with any deep neural network, there are hyperparameters. And one of the hyperparameters we have in an embedding layer is how many embedding dimensions, how many hidden units do you want in that layer. Higher dimensions are good because it allows us to tease apart more distinctions, and therefore we can learn better relationships. On the downside, as I increase the number of dimensions, there's also a chance of overfitting, and it's going to lead to slower training and the need for more data. So a good empirical rule of thumb is the number of dimensions to be roughly the fourth root of the size of my vocabulary, the number of possible values. But this is just a rule of thumb, and with all hyperparameters, you really need to go and use validation data and try it out for your problem and see what gives the best results. And embedding can also just be thought of as a tool. One of the things we get from these embeddings is we map items, movies, text, for example, the words in the housing description, to these low-dimensional real vectors in a way that similar items are nearby. It creates structure into these items that really we didn't have any structure, and the structure is in fact geared towards what you're trying to do with it. We can also apply embeddings to dense data. For example, if I look at the way audio or soundtracks are represented, it's already dense. But we don't have any meaningful metric. I don't know how to say this audio is similar to that. And so we can use embeddings just to learn a similarity metric among already dense data. And even further, we can embed diverse types of data, text, images, audio, jointly, and learn a similarity metric across them.
So far, we've spent a lot of time talking about how to build models that do a good job of predicting on new, previously unseen data. And this is, of course, the heart of any machine learning system. But a machine learning system needs to be able to make predictions that influence the real world. And to do so, they need to be part of a much larger ecosystem than just a little black box that does machine learning. If we look at a full machine learning system, it includes many components that are not about training. For example, we need to have data collection, we need to have feature extraction, data verification, various forms of monitoring and data analysis. We also need to get these things out to serving so that they can make predictions that are used in the real world. Now, these are a lot of different pieces. Fortunately, you don't have to build all these pieces yourself. There's a large number of components that can be pulled off the shelf and used in your application setting. But how do you know which of these components are the right ones for your particular task? Turns out that there are a couple of key design choices we can look at that will help guide these choices. We'll take a look at these now. One key consideration when designing a machine learning system is whether we do training in a static way, offline, or dynamic way in a continuously updating online fashion. Now, when we say static offline training, what we mean is that we essentially have a big store of data and we train our model exactly once before it's used for a long period of time. When we talk about dynamic online training, we mean that data is continually coming into our system and we're incorporating that data into the model through small updates. These both have different strengths and weaknesses. Now, for a static model that's trained offline, there are some definite pluses. It's easy to build and test. We can just use batch quota, it's nice and cheap, and we can iterate on that model until we know it's good, it's nicely verified, and we can make sure that everything is working well before we ship it off to serving. The downside here is that it still requires monitoring at the input level at inference time. If our distribution of inputs changes and our model hasn't adapted, well, we may end up with screwy predictions. In a similar vein, it's easier for this model to grow stale. You might imagine if a model is trained on pre-iPhone data and suddenly the iPhone comes out, there's no good way for us to get that information into the model without accounting for some kind of retraining. A dynamic model that's trained in a continuously updating fashion, of course, has much more sort of heavy weight in terms of monitoring. We need to have more system complexity and larger monitoring capabilities in order to make sure that this thing isn't going off the rails. The plus side for all this extra work is that we have a model that's able to adapt over time as new data comes in. And so we don't have this staleness issue. So a good place to use offline training is when we don't think that our data is going to change very much over time. An example for this might be a large image recognition model, where there just aren't that many new kinds of objects that come into the world. A model that's trained online might be more appropriate for situations where, in fact, there are trends and seasonalities that change quite often over time, and we want to make sure that we're as up-to-date as possible. Another important design consideration when we're designing machine learning systems is whether we do inference in an offline or an online fashion. And by inference, of course, we mean making predictions. Are we going to do this once offline and write those predictions out to some table or some static place that we can then read from? Or are we going to do it continuously on demand with our models stored in some server and predicting on new data as it comes in with new requests? Well, again, these have different strengths and weaknesses. If we're doing offline scoring, then we get a really nice opportunity to do post-prediction validation. We write out all our scores and we can sanity check that these scores make sense before they're used to influence the real world. We also don't have to worry quite so much about computational costs. If our model is expensive, if it takes a lot of cost to compute our predictions, well, we can just throw more machines at it, maybe using batch quota or some giant MapReduce, not have to worry about things too much. The drawback to offline scoring is that we need to have all of our examples in hand at the time that we're doing those predictions. So for areas where we might have a long tail or some crazy distribution that's changing on us, we might not be in such luck there. But if we know in advance what all of our examples are going to be, or we only care about head queries, something like that, then we can stick those all in a nice offline scoring lookup table. For online scoring, remember that we're putting that model into a server and then querying that server on demand. Now this is great because it means that for long tail situations, any new example that comes in, could be crazy, whatever, we can still get a prediction for it on demand. However, the latency issues are something we'll need to think about. A lot of situations are latency sensitive, so we can't take more than 5 or 10 or 50 milliseconds to make our predictions, which means that if our model is expensive to compute, we might have to throw a large amount of production level resources at our jobs. This can be expensive. We'll need to budget for that. The other thing to think about is that we may need to increase our game in terms of monitoring. Not only do we need to monitor the serving jobs themselves, but we also need to monitor the output distributions of our predictions to make sure nothing is going haywire. So again, there's pluses and minuses to online serving. So let's talk about data dependencies. And by data dependencies, I mean something very akin to code dependencies. When we write software code, we want to include as few external dependencies as possible. Same thing happens with machine learning models. We want to include as few data dependencies as we can. Now, by data dependencies, I of course mean our input features that we use for training and for prediction. Our input features are important because they determine our system behavior. If our features change, our system behavior will change as well. Now, in software engineering land, we know how to test code. But features basically take the place of code in our machine learning systems. And we don't necessarily have a great analog for unit tests of data. So we need to be very careful and basically go through a checklist to make sure that we're including features that are useful and will not hurt our system in the long term. The first question is this piece of data reliable? Which is that, is this signal that I'm incorporating going to always be produced in the same way whenever I need it? Now, in some cases, an upstream signal might be flaky. Maybe it comes from some server that is only available 95% of the time. If it's not available, we need to have a fallback plan. Maybe it looks like an indicator feature that shows that that signal was not available as a Boolean. We need to think about, is that feature going to change on us over time? And do we need to think about the versions of it? It's easy to imagine that we might have a signal that comes from some upstream model or some upstream process that changes over time. Whenever possible, it's good for us to either have a version number imported to us so we can know when that upstream signal changes, or to actually take ownership of a copy of that signal and only update that signal on our own schedule. We want to think about the necessity of these features. Oftentimes as machine learning people, we get really excited about improving the accuracy or the quality of our model, and we end up finding sort of areas of diminishing returns where we add a tiny little epsilon of benefit at the cost of 1 or 2 or 10 different external features that we're now depending on. And we want to really weigh these costs carefully. Are we getting enough bang for the buck when we add in a new feature to really pay for the long-term maintenance costs that we're adding to our system? We also want to think about correlations. Is this feature, in fact, something that we think is causal, or is it just something that happens to be correlated, and would we know if those correlations changed? Now, one way that we might tease apart these correlations is by injecting randomness into our system to sometimes tease apart these things. This sort of randomization is an important strategy. We need to think about feedback loops. As we said before, we'd like to make sure that we don't have non-stationarity in our system. The easiest way to get non-stationarity is to have our input data depend on the outputs of our model. Now, this can happen in interesting ways. One of my favorite examples is in the world of stock market prediction. You might have two stock market prediction models from two entirely different firms. If one of these prediction models has bugs, it might cause stock market prices to go up on a certain stock. The model from the other firm, from firm B, might be looking at this and will learn from that data and may also exhibit changed behavior. So the bugs from system A may in fact change the behavior of bugs from system B, even though those systems are completely disjoint and are in fact from completely different companies. So feedback loops are a real thing, and we need to find ways to track them down and account for them. So let's look at a real-world example of a machine learning system that had an interesting issue. So this was in the case of cancer prediction. There was a model a couple years ago that was trained up to predict the probability that a patient had cancer from medical records. So in those records, we extracted features, things like patient age, gender, medical conditions, hospital name, vital signs, test results, all that kind of stuff. And the folks who were training this model felt like geniuses because once they trained that model, it gave outstanding results on their held out test data. And they were extremely careful not to mix any test and training data. However, when they applied the model to new patients, the model did terribly. Couldn't figure out what was going wrong. What could have happened there? Well, here's what happened. One of the features that was included, as we said, was the name of the hospital. Some of those names were things like Beth Israel Cancer Center. Turns out that that's an extremely useful indicator to know if the patient in consideration, in fact, is suffering from cancer. Now, even if that string didn't contain the word cancer, it's the case that many hospitals have different specialties. So some hospitals specialize in cancer treatment, some do not. Even if you were to take that Beth Israel Cancer Center and turn that into an anonymized integer, there would still be many patients that were strongly correlated with that particular hospital because that was a hospital that specialized in cancer treatment. But for new patients that haven't been assigned to a hospital yet, we don't know that information. It turns out that showing the model the name of the hospital is a subtle form of cheating. It's a subtle way of exposing a doctor's diagnosis to the model in a way that they wouldn't have available if they were trying to be acting in place of the doctor. So we call this label leakage, where a little bit of the training labels leak through into the features and allow the model to cheat. This is a classic failure mode that's important to avoid. Let's take a look at another interesting machine learning system that had a little quirk in it. So we were working with a professor of 18th century English literature who had developed a database of metaphors of the mind. Basically, he had gone through all of 18th century literature, and every time an author had said, the mind is a garden, or the mind is a blank slate, he had written those down in a database. And he was interested to know whether the metaphors of the mind that an author used were indicative of their political affiliation. Well, it seemed like this is something we could test using machine learning. We'll build a model, see if we can predict these things. So we did this. We created a set of training and test data where each example was one metaphor of the mind that an author had used and the label of the author's political affiliation, Whig, Tory, whatever they did in the 18th century. We divided those up sentence by sentence into test, train, and validation splits, trained up a model, and found that our test validation accuracy was incredibly good. It looked like we could indeed predict an author's political affiliation based only on their metaphors of the mind. Total success. Except then we looked a little deeper and realized that maybe our accuracy was actually suspiciously high. Was there anything here that was going wrong? Well, one of the things that we noticed was that when we created our test, train, and validation splits, we did so by dividing up our examples sentence by sentence. And so if we looked at, say, Samuel Richardson, some of his sentences would end up in the training data, some in the validation data, and some in the test data. This meant that the model had the ability to learn specific qualities about Richardson's use of language beyond just the metaphors that he used, and in a sense get to memorize a little extra stuff about him when it came time to be applied at test time. We ran another experiment where we divided things up at the author level, so that given authors were only in the training data, or only in the test data, or only in the validation data. And when we ran the experiment this time, we found that it was much more difficult to get good accuracy on test data, and thus much more difficult to predict the political affiliation based only on the metaphorical data. So this was kind of interesting. One thing was we got to write 2 papers, one with each viewpoint. The second was that we learned an important lesson about how critical it is to think about the ways that our training data and test data are randomized for these splits. As a machine learning person, it's easy to think, well, we'll just randomize the data, but we actually have to know what the data represents in order to create these good splits. So to finish up this session, we want to think about some effective machine learning guidelines. But when you're going off to create a machine learning system, please keep the very first model extremely simple. A simple linear model is absolutely the place to start so you can verify the pipeline correctness. And you want to make sure that the data pipeline is in fact fully correct end-to-end before doing any iteration on model quality, because bugs in the data pipeline will be extremely hard to track down later on. You want to use a simple observable metric as your first thing to use for training and evaluation so that you can verify that the model is behaving as you expect. You want to own and monitor your input features as much as possible. You want to treat your model configuration as code and make sure that anytime you configure a model that is reviewed by a teammate and checked in. Make sure to write down the results of all your experiments, even failures. Documentation is incredibly important for later debugging.